under which Hamiltonian or which initial state this rate can be maximized. This will not be our situation because for us the initial state is one where A is only correlated with A bar but is not correlated with B. So for us this thing is actually 0. So the expectation is that if we just plot this mutual information against time, the expectation is that something like this will happen. Something like that. Basically there is at small times, this goes like this square. And it's completely generic. It's just a consequence of the fact that there is no correlation between A and B. Then we expect some growth, which is on average, in some average sense, is roughly linear. In other words, we expect this at intermediate times and for quite long times to be essentially constant. I just want to stress this fact, we don't expect this to be always constant. It's in some average sense constant at intermediate times, and then after some t, which we call t star, somewhere here, the mutual information will essentially saturate. Furthermore, what Steve conjectured is that in interval of times, this constant rate will be essentially given by the energy scale times some constant k times the sum of the squares of the couplings. So this is the conjecture. Okay. So we don't know how to show that this is true in full generality. I mean, this is the big question, and we would be very happy to discuss with anybody who's interested. But let me just give you, let me just show you a simple example where you can actually see that something like that might happen. So the intuition for this comes from the picture I had before about the decay of system A when in a large environment B due to small interaction, and it comes essentially from Fermi-Goldberg rule. So the decay rate for unit time is, this is just Fermi-Goldberg rule, it's just given by this interaction, and this is just the density of state. So it's roughly constant in time, and it depends on the interaction terms this way. Of course, we have a slightly different situation here because our initial state for A is a mixed state, but that doesn't really play any major role, as I can show you in a simple example. So let's say that we have a qubit, a single qubit, so A is just one qubit, and B is large. And A bar, we are always assuming that A bar is the same, the Hilbert space of A bar is the same dimension of the Hilbert space of A, so this is also one qubit. And consider the following evolution. So suppose that we have an initial state on A, B of this one. Let me ignore A bar just for a second. So 0 here means some initial state for B. It can be anything. It could be the zero energy state, but it could also be something of higher energy, as far as transitions are allowed, so that A can still decay. And let's assume that this would be with some probability, which depends on time, nothing happens. And with some probability, this qubit will actually decay. So, t, 0, I. And then if instead the initial state of A was 0, by energy conservation, nothing happens. The state will remain the same. Now, this thing here, well, or more precisely, this is the probability at time t that this qubit A will actually decay, and alpha t modulus square is 1 minus p of t, is the probability that it doesn't decay. And in the simple situation, it's straightforward to write down what the final density matrix for AB at time t will be under the assumption that the initial state, let's say psi A bar at t equals 0, is just maximally entangled. State. You can consider anything else, but for example, let's consider this one. I won't write down the full expression, but let me just write down what the reduced density matrices are. So it's straightforward to actually compute this. So the reduced density matrix for A under this evolution is 1 half 1 plus P of T 0, 0 plus 1 half 1 minus P of T 1, 1, and it will be where this thing here is a unnormalized pure state. Actually, psi prime is just this. So from there, where is it? to compute the fundamental entropies that we need. As I showed before, as I showed here, we don't care about we just need the fundamental entropy of A and B to compute the mutual information we want. And final expressions are the following. So this is minus 1/2 P of T. If you look at this expression, you can immediately check that if you assume that the initial time, the probability at time equals 0 is 0, then you can immediately check that the entropy of A, that this is correct, as it should be, it was just a single qubit, and the entropy of B is 0, as it should be, because B is not correlated initially, so that the initial mutual information between A bar and B is 0. At a later time, so let's say that for large time, let's assume that the probability of decay at large times is close to 1. Then you can check that the entropy of A is and entropy of B now is log 2. So that the mutual information between A bar and B now is 2 log 2. So that we are in the situation basically that we want. So you can what you can do, you can basically do, for example, some numerical check. You can just numerically consider a state where a system where A is a single qubit and B is like 2 qubits, like 7. And you can just evolve things numerically. You can compute these probabilities numerically. You can actually, so you can compute numerically the probability of decay and use these two expressions to plot the mutual information, how the mutual information time. Or you can just ignore this expression completely, just do numerical evolution and directly compute the information between A bar and B and compare the two equations. You can actually see that at least in this very simple setup, the two different calculations match very nicely. So in a simple example like this, the simplified model of evolution that was explored and how I erased is actually a very good approximation to what really happens. So this is not very strong evidence that the conjecture is true, but it's some evidence that at least in some simple setup, it could be true.
Okay. I didn't follow what you actually just verified. You verify that your calculations were right, not anything else, so I missed it.
Oh yeah, so these two formulas here come from this simplified model of evolution that I had in the book.
What simplified model?
Right, so the thing I was, for example, disallowing transition with binary energy conservation, like from 0. I was neglecting some terms in the evolution. The expression I got before. No, that is not. Okay, so that's the point. Yeah. So what I was writing down is that, for example, if you initially have the state 0, 0, this will exactly transition to 0, 0. Which doesn't have to be the case necessarily. Of course, this is strongly, this is essentially what will happen by energy conservation. There might be some probability.
Yeah, what are you assuming about the energy spectrum of the second system?
Of the second of system B, I'm assuming that the spectrum of B is very dense because the hyperspace of B is much larger, and that the spectrum of the Hamiltonian is such that the transitions from A to B are allowed nicely, so that the A would keep it decay. Which doesn't have to be if you just take arbitrary quantum systems. The transitions might be disallowed, for example. If I just cook up some Hamiltonian with energy levels that I can choose as I want, it's not necessarily the case that that qubit can decay. So okay, and then there was this evolution, but this is not the most general evolution that you can write down. So these two formulas in principle don't have to match what is really going on. So if you just take a system of 1 qubit for A and 7 qubits, that's what we did, for example, for B, and you just generate random Hamiltonians, no reason to believe that this simplified model of evolution will actually match what you would obtain numerically by doing exact evolution just numerically. But what we actually verified is that these two formulas give a very good approximation to what really happens, and therefore you can trust them.
And so in some sense you're supporting the decay, the simple decay.
Yes, exactly. For small coefficient C, in fact, look, so if you use large coefficient, the two pitches won't match. Yeah, exactly. Yes, you're in a situation which is similar to the one unitaries between A and B. Exactly. Thanks, that's a good point. Okay, so we also verify that you obtain a picture like this where you can just compute what the rate is and you can actually check that the rate does in fact depend on the square of the couplings with this equation. Then you can also cook up some other models which are slightly more general than this, where you don't have a single qubit in A, you have more qubits, and again you cook up some evolution, here's a more general picture where you have more levels in A, and you can see that things still match, but what we would like to have is a more general explanation for why this has to be true and under what condition this exactly is true. I don't know how to do this. I just want to mention one possible direction. Actually feasible, but I think it's interesting. So I have no idea how to prove this, how to prove that the decay rate is essentially given by this expression. But one thing I want to try to do first is to actually try to show here. Depends goes basically like 1 over sum of ci squared. So this will not necessarily automatically prove that the rate is constant. Depends on the couplings in this fashion, but if you can show that this time this star essentially depends on the coupling in that fashion. So one possible way to do this, I think, might be to use a theorem by Short and Faraday, 2011. This is a general theorem about equilibration of finite systems in finite time in an approximate sense. So I just want to mention what the theorem is. The theorem says the following, that given some small energy, I'll explain things in more detail in a second, but given some small energy, epsilon, and some time t, the following rho A is the same thing I was mentioning before. This is just a reducing matrix of A. So this is a completely general theorem. So, and this will be okay. Let me call it S. You can imagine any system, and which is evolved by some Hamiltonian subsystem S. And this was a general theorem about any possible situation you can imagine, but for any possible subsystem S. Omega S is the time average of rho S from 0 to infinity. So the statement is a statement about the distance in trace norm between the actual the subsystem S at time t and its time average between 0 and infinity on average in time in the so this is the time average from 0 to capital T of this trace norm. And the result is that this is 1/2 square root of T S squared n of epsilon, which I will explain. This is something that depends on Hamiltonian. dA. So here ds is just a dimension of the Hilbert space of subsystem S. df is a number which depends on the initial state. The point is that this is a theorem not about thermalization, it's a theorem about equilibration. So there's still information about some dependence on the initial state. This is what we call the effective dimension of the state, which is just defined as follows. Trace of Pn rho 0 squared. So rho 0 is the initial state of the full system, not just the subsystem. And Pn are the projector the energy eigenspaces. So the Hamiltonian here is just sum over n, Pn en. So this is the only dependence on the initial state enters, this number here. Then dE is the number of the in Hamiltonian. And n of epsilon is what they call the density of energy gaps. Which is defined as follows. Let me write it here. Maximum over all energies of the G. So given some small number epsilon, you look at the energy interval E plus epsilon, and you look at all possible such energy intervals, and you maximize over them. And you look at